Before I start, let me see what kind of audience we have here today. Who has, I want to see the hands, who has Flink in production right now? Perfect, very few. So those who has in production or who are like experimenting with Flink, how many operators do you usually have? From 1 to 10 operators? All right. Anyone from more than 20, 30, 40 operators? No one. Okay. So that's what we're going to do today. My name is Oytun. I'm the CTO of MotaWord. At MotaWord, we're doing human translation in 90 languages. We're doing this with around 17,000 translators spread around the world in 200 countries. We're doing everything very instantly except the translation experience itself, and our core model is a model called collaborative translation. So imagine all of us together in the same room and we're working on the same document. We're translating it from German to English. So we collaborate with each other, we talk to each other. That makes our process very fast, about 20 times faster than normal human translation process. And where does Flink enter into this platform is we're doing user behavior management with Flink. So basically complex event processing plus some data processing a little bit. We're automating through Flink and some other components. We're automating many of the human tasks apart from the translation act itself. We're everywhere. This is what our web platform ordering page looks like. This is our client dashboard where you can track your projects in real time. This will be our translation editor, so multiple translators are coming here and they can see each other, kind of like a Google Docs experience here. Again, we're everywhere. We have an extensive API with plugins and extensions, so you can imagine the data pouring in into our PAM. We used to call this IPM for Intelligent Platform Manager. Now we're trying to humanize it because the interactions are actually very human. We're trying to do some contextual analysis and reactions here. Some examples you can see here that Flink helps us do. We're detecting anomalies in the translator speeds, in project delays, or whether we need a proofreader for that specific language pair because we observed that in the last 2 months we had a little bit of delay, or the platform just kicks off unresponsive translators if you're not responding to our, I don't know, emails or push notifications for a certain amount. Or the last item, the contextual project invitation, is what we're going to handle today. Basically, we don't want to send out invitations to 17,000 translators, but we want to send out to a very specific segment that maybe has been online in the last 5 minutes, or that are not on the go on their mobile phone, so they're not changing their locations right now. Those kind of things, and we're using Flink to do this. So we're not talking about big data, we're talking about tiny bit of data, tiny bit of state. This is what our Flink execution graph looks like. So typically, in my experience, I started exploring Flink 2 years ago. Mostly just a couple of operators, or at least up to 10 operators at most. But we have 75 operators right now, replicated into 400 tasks, and we're doing all of this in a single job with a very small state. Our state is in megabytes right now. Today, we're going to do this. We're going to take the graph up there, and we're going to arrive to this graph by refactoring an entry point into multiple modules. And we're going to do this to establish our business domain in the code base, because if you're not using primitive data flow primitives, and you don't want to use them as an application developer, you really want to establish your domain in the code base so you can onboard a new developer very quickly, and they can just take that arbitrary object and just start using whatever stream or state we're talking about without all those kind of complicated, kind of conflicting broadcasting and curable state mechanisms. So we're going to apply broadcasted state compulsorily in every business object, and we're going to make all of our state curable by default. So those are some of our constraints in this kind of application. We only want to do stream no batch, nothing, and we don't want to block anything, so everything just flows downstream. And all of those streams are broadcasted into operators so that we have consistency in our parallel operators. And as I said, we're going to make all of our states curable, and we're going to do this in a single code base, in a single job. We don't want to refer to any external data. So you can also, if you read some articles this year, there were some Flink articles about using Flink as a database. So we're also doing it at the same time, actually. And all of our objects that we will talk about are going to be referable, so they will be public API, actually. So let's set the ground. This is a simple entry point, our streaming job. This is our single job. We start here with the environment. We have a default source, and we filter the source for a very specific event, proofreader taking project. So the business logic we're going to work on today, we have clients and we have proofreaders, and proofreaders work for clients. So we want to keep in our memory, in our mind, that these proofreaders worked for this client in these language pairs, and when a new project comes, new translation project comes, we're going to get those proofreaders, maybe with some filtering and some constraints, and we're going to invite those specific proofreaders first before reaching out to the wider vendor base. So that's what we're doing here. We're first building our proofreader list, filter the source, process it to convert into a business entity, which is the client proofreader entity here. And we take the client proofreader stream, key it by the client and the language pair, and we window it. This is actually not needed. It's for backfilling purposes. It helps sometimes. Especially if you're triggering something immediately as a reaction, you may want to window your backfills when the application boots. And then we're going to send that stream into an accumulator so that I have a list of proofreaders, actually, not just single items flowing downstream. And then we're going to just do something random with that proofreader stream. So this is the typical flow. Let me quickly dive into were you able to see the details? I'm not sure, but let me zoom in here. This is the filter. This is the accumulator, the entity conversion. Accumulator turns a client proofreader into a client proofreader list and then does something with it. This is what the accumulator looks like. If you've implemented anything in Flink, in your second day, you will probably hit a process function. This basically turns a single item into a list and keeps it in its memory, and do something, just does nothing, actually. We're going to refactor this to arrive at a better business organization. First, this is our new entry point. So we removed all of those source filters, entity conversions, and everything, and we moved them, extracting them into an arbitrary object called client proofreaders. And from now on, I'm going to call these arbitrary objects business operators. In this session, I'm kind of competing with the stateful functions that they just announced today. I think that's a very good direction for Flink to go ahead, because we're steering away from data processing, because now the norm is data processing. Now we need to start talking about applications. This is what our arbitrary client proofreaders business operator looks like. Now it simply takes a source stream, and then it has this run method that does exactly the same thing. And you can see here, it keys, it processes, creates a list, and it just continues like that. None of this had any impact in my execution graph, because all of these are syntactic changes, actually. So even initially, we took the source, did some things, and that was it. So we lost the stream, actually. So now we started sharing our results stream with those arbitrary methods again, get results stream. And this is what our entry point now looks like. So very isolated. I have a client proofreader that takes the source, I run it, and then I use the result stream somewhere else. Now we have two new operators. These are do something operators. And if you pay attention here, we're just forwarding this stream to those operators. Now, we want to, so these two do something operators are very simple operators. That's not how we usually consume our streams in real world. So we're going to start the second phase of our business logic where we get the new translation projects and we match it with the client proofreaders and invite the proofreaders to the project. So again, I start from scratch, get the source filter for project created, new projects basically. I key the projects, connect our client proofreader's result stream, and then I process them in invite last proofreader. So invite last proofreader basically becomes a keyed co-process function because there are two different streams, two different types. We're running a co-process function. So if you look at here, process element 1, process element 2, the one takes a new project, and the second process element 2 takes the last version of the client proofreader list, and they will do some business logic there. So one thing to draw attention here is this state. My invite last proofreader operator, which comes like, I don't know, 10, 20 lines after the client proofreader's object, it is actually keeping a state about client proofreaders, and it uses its own key. It can manipulate the value that it's keeping in its state. So the problem here is my domain information is organized and stored by something downstream that I have no idea about. So I cannot really put limitations to my developers that, hey, this is how you need to access, this is what it means to be a last proofreader of the client that you're going to invite. So there are no business constraints in this kind of scheme. And the truth, the item that we're generating above in the client proofreader's business operator, it is actually constantly replicated in all of the downstream operators, and the replication method is unknown to the upstream operator. So we don't like this. It is very decentralized. Yes, of course, the whole point of this parallelism, the clustering, etc., is actually to decentralize. But in real world, you want to have some kind of abstraction when you're having 75 operators to begin with. And we expect the number of operators to reach 200 operators till the end of the year. So now we have a curvy line here. We're starting, this is the new projects filter, and we merge it, we connect two streams, this one and this one, into this invite last proofreader. All right, so a way to prevent that duplicate truth situation a little bit is to broadcast your stream into local state. This is a must actually when you have parallel operators keyed differently. You have to broadcast your stream so that all of your downstream parallel operators can have the same state almost at the same time. Right. There may be, of course, a little bit of delay in between the operators, but this is how you will typically broadcast. So this is our arbitrary client proofreaders. We run it. We have a descriptor now for any state. Descriptors all over the place. We get the result stream and we broadcast that with that descriptor. And now, instead of connecting our resulting stream, now we connect the broadcasted stream. So this makes our invite last proofreader a keyed broadcast process function this time. Excuse me. Now just a couple changes here. Process element 1 removes the 1 at the end, and it now has a read-only context to access the broadcast state. And we also have a new method, process broadcast element, that basically takes the broadcasted stream and again stores it locally. So the storing decision is still done in this downstream operator without the knowledge of the upstream operator. Again, which scatters our domain information here. So this is what our new execution graph looks like. Now, this used to be forward, now it is broadcast. I really enjoy using broadcast, but it's a little, you will see it gets really crowded and you have all those map descriptors all over the place. Normally, typically you can see this map descriptor with a key of client language pair and the client proofreaders list, which is actually generated here. So I define this outside of context. Who knows what's going to happen there, right? It's in the public park, and I don't know what's going to happen to that map descriptor later. And this one, you need to go back to change the code, actually. So let's simplify this a little further. I'm going to extract this part, just like we did with client proofreaders. I'm going to extract this part into its own arbitrary business operator called invitation. Now it takes a default source to create the new project stream, and it will also take a broadcast stream from outside. And it has the run method that filters, does that, this, that, and then it will share the resulting stream. So now we have two arbitrary objects that look very similar to each other. And this is what our new entry point will look like. But this map, this broadcast decision, this map descriptor, which is still outside of the realm of client proofreaders, is still bothering me. Again, that was a syntactic change extracted into the invitation module. There's no change in the graph. I want to go through these items because this is why we are doing what we're doing actually. So data flow is, by its nature, is a physical move of data actually. So we can't do anything about that, and that's why we prefer data flow programming. But we can do some things about these green ones. So we want to abstract more. We don't want to duplicate our concepts. Their consumption is okay, but their generation and their distribution should not be duplicated. And this is very connected to the truth situation. I don't want any duplicate truths to be generated about a single human concept. This makes me feel very weak when I'm walking around the code base, and it prevents me from establishing my domain and transfer that knowledge to other developers. To prevent that, we're going to give the broadcasting responsibility into the generator of that information. So we're moving the broadcast descriptors and the broadcast decision here back to the client proofreaders. So now client proofreaders has these extra methods to share the broadcast stream and share the broadcast state descriptor. This is what the entry point now looks like. I have client proofreaders that generates information, shares the information, and I can use it in this way. So I can just get the broadcast descriptor, and I can just get the broadcast stream. So invitation, now it doesn't take a broadcast stream anymore. It takes that arbitrary object, client proofreaders, and it uses get broadcast stream to connect into its own operation. So I want to exaggerate this a little bit. So yes, you are connecting this broadcast stream into your invite last proofreader. So your last proofreader operator actually still has those process broadcast elements, and there's no way to work around that. But I can forward that manipulation of the state back to my arbitrary object, just like this. So you will. Not sure if that red line is read properly, but you will typically get this context, get the broadcast state, and put this incoming item into your broadcast state. Now I don't want to do that, because if I do this, I need to decide which key to use, which value to use, how to keep that state, what kind of business operation I can do that. All of that information will be contained in this operator, which is far down in the execution graph. So instead of doing that, I'm forwarding whatever I'm taking here, I'm forwarding it back to client proofreader's arbitrary object, which now has it has the same name, but it's just a convenience method, actually process broadcast element. So what this does, it will decide for me is invite last proofreader, it will decide for me how to keep this state in my own context. And in a similar way, now in the process element, in my real business logic, I'm also using client proofreader's object to do business operation, pick last proofreader on that broadcasted stream. So now this whole operator has no information about client proofreaders, but it uses client proofreader's object first, just to get it sugar-wise, and then also apply business operations such as pick last proofreader onto that. So this makes me feel a little better, even though some of these are just holding the ear from the other way around. But I'm not very bothered with that kind of syntactic indirect manipulation, let's say. So this is nothing changed in our streaming job entry point. And nothing changed in the execution graph. So what did we do so far? We generated truth, we shared the truth, we broadcasted the truth, so all of the parallel operators with different keys will have the same data. Now we want to open this to the public, because what is an application? You run you generate the data, you manipulate the data, and you make the data available internally, also externally. So now we're going to make this insight or data, let's say, available outside. I stole this from Ufuk's presentation in 2017. Queryable state is really tricky initially to understand, because there's a gimmick. Queryable state is an external concept. You cannot access queryable state within your Flink execution. It is an external concept that you basically use an SDK, query client, to send requests to your Flink program that is running already. So this is gonna make, this makes the understanding of how to access the state a little weird, and that's why actually, if you were in, what was it, functional, stateful functions, I don't know, somewhere there, they suggested, the worst practices, they suggested, not to use QS, queryable state, for production, which we do. We do everything naughty here. So yes, you have the query client, but now we wrap it around the REST server actually, so that I can take JSON HTTP requests, convert them somehow, and make a query in my Flink program and access my value. So this is how you would typically do a state query in Flink. So you would use the client, the query client given by Flink, and you would use, all of these are explicit, strongly typed objects. So all those strongly typed situation makes our life a little difficult. Now I need a state name. I need the value of the key that I'm looking up in the state, such as client ID 1, language pair German, English. And then I need to give the type of the key that I'm looking up. And then I need to give the descriptor that I'm going, the state descriptor that I'm going to look up at. So many things happening here. So this is gonna mean you need to replicate your domain all over the place. So if you remember the map state descriptor that we initially used to broadcast our state, it was in the entry point. So very similar situation. Now you will need to move that map descriptor into this code base too. So we don't want to do that. Instead, we are implementing a new interface that we call abstract business operator. This is not a Flink primitive, so don't look up at the documentation. Now, client proofreaders operator, business operator, extends this, and now it has this convenience methods. This is completely sugar. It just shares the state name now, state key type, and the state class. This really drove me crazy, because you cannot access class from type hint. So you just need that sugar again to share your shape information with the external world, so you can broadcast and make them queryable at the same time. So this abstract operator does some things automatically. Whatever state you're creating in your business operator, and all of them are now broadcasted automatically, and then they're also made queryable automatically. And now, the way that we query this state is also implemented within the abstract operator by default by using these helper methods. So whenever I receive a JSON request from outside like this, now I will use this method to convert this JSON into the state key class, so that I can use it to query my key, my state. And then when I get a response there, I have no idea what kind of response I'm gonna get. I can get a map state, I can get a value state, whatever. I'm going to convert that state into back to JSON. So in all of these examples, I'm using map state because there will be some type conflicts that we will talk about briefly. As I said, queryable state is an external concept to Flink, and you basically need, if you need an HTTP interface, you need to build that up, and you use the query client to query the Apache, the Flink execution. This is what our very simple state server looks like. It prepares the routes. This is very interesting. I enjoyed it a lot. What it does, it scans all of our Flink code base. This lives in the same code base for this annotation. And now every business operator uses this endpoint annotation to say, hey, open me up, open my queryable state in this endpoint. And our REST server code scans all of these business operators, finds those operators, and opens them up in this endpoint and calls their query method. So streaming job, entry point, nothing changed. Did I go back? Yeah, nothing changed. And this is our #1 application, the Flink program that we're running. And at the same time, we're going to run another program for the state server. And this is what it looks like. See, it scanned and it found this, opened up this object for this endpoint, and now I can actually send a request. This is what the Flink is running like. No changes in the execution graph. I think these things, of course, this is an execution graph. This is not a program graph, right? So maybe we could have an alternative graph to see the broadcast and query relationships better here. Most of these things, I think we achieved briefly. This is a watered-down version of all of these concepts that we want to achieve. Now we can make a request. So this is my key. I have a client ID. So basically what I'm asking is, give me the list of proofreaders for this client in this language pair. And the response I get is this. So if you're new to Flink, get ready for this kind of errors, because they have a deeper reasoning actually behind them. Remember, everything's strongly typed usually in your Flink program, and the way the broadcast stream works, broadcast state pattern works, you cannot query that state. So why did I take you until here just to show failure? Because it happens to me all the time. You will see this kind of state type conflicts in various operations when you're using Flink as an application framework rather than just throwing billions of records just to do data processing. So you can only broadcast map state. You cannot broadcast any other state. But then your operator can only manage list state unless you let Flink manage the state for you. And you cannot query the broadcast state, but you can query only the keyed streams, keyed states. So if you merge them, if you want to do all of these together, you know, they don't really have a common denominator there. To do that, we're going to do a very ugly hack. We had to do this because we were like this close to production in this specific workflow. Now what we're going to do, we're going to if you remember the run method from client proofreaders, now it's calling this new method queryable as value map. You won't believe what we're doing here, but we're duplicating the stream actually so that we can create a whole new state that we can query, right? So this is what it looks like. Basically, now we have this new operator, accumulate map value. It's a very basic flat map operation, and we key it, and then we flat map it into this operator. And the operator basically just takes the object and puts it in the state. That's it. This is opened by default for our query. How? Because we're using exactly the same descriptors, exactly the same key types that we initially defined in the business operator client proofreaders to generate our information in the first hand. So it gets a little ugly here, and this is what our new execution graph looks like. Now, this is the duplicate operator. At least it's hashing, and then this one is just logging, and then we also broadcast it at the same time. So there's two-head situation here. I wouldn't say this is 100% healthy, but this is currently the only way that we achieved broadcasting and queryable at the same time. And when you don't have billions of records, you don't really probably have much concern about this duplication. We still have state in megabytes. Now we can make a request. So I still do exactly the same request because we use the same descriptors in our duplicate flat map operator. Now we're able to get the list of proofreaders. No changes in our streaming job, and you can see how clear it reads. Client proofreaders, run. Invitation, take client proofreaders, run. Very simple reading for humans. So I'm going to close this up with a quick summary. We're only using stream. Well, this is our basically company constraint. We only want to use streaming. We didn't block anything. Everything is shared with the getResultStream method. Every stream is broadcasted by default, because if you don't broadcast, your parallel operators with different keys, they will not access properly. All of our states are queryable now, a little hacky. Everything is in the single code base, meaning our queryable state server and the Flink lives in the same code base because they use the same types, strong types. And we didn't refer to any external DB to make queryable state possible. So our external application, your web app can now actually query the state and use some information out of it. And all of our objects are shareable now. They're shared. Again, drawbacks that are fun to play with. I love refactoring stuff. Strongly typed everything is a problem that's hard to go around. We have some conflicts here. Again, there's no common denominator in the list state types. So you will need to really sit down, get a cup of coffee, and think how to store your state. That's very, very important. I would love a unified queryable broadcast state so that we don't need to do any of this, because an application really needs this consistent data through broadcasting, referable data, and also public data to call it an application. Some people may be bothered with this, that the queryable server code actually lives within the same code base. I really enjoy it, and we have to do it. People have been asking, what do I think the future of Flink looks like in means of application implementations? I think we can optionally let people sacrifice decentralized structures a little bit, so we can have a little bit of centralization, like broadcasting kind of things. Could be easier with a little bit of centralization, and which is, possibly coming with the stateful functions. I find this kind of pattern with stateful functions, they're very complementary. It could be better with a little bit of, less boilerplate. This is interesting. I've been thinking about this a lot. I would really love if we could extend the UI component, and Flink actually has a REST server in the code base, but we can't use that. I tried to use their REST implementation to open up the queryable state server. Didn't work. That could be done. This ecosystem is coming up. I'm not sure if the team released the public version, the ecosystem website.
Very soon.
Very soon? Perfect. Did I break the surprise or something? But this is one of my wishes. I can foresee now, to me, stream processing and data processing is a given. Now we can extend and do some plugins on top of it. I imagine Facebook releasing a public, of course, public or encrypted stream, making it publicly available, and also providing some extensions and plugins on top of Flink so that maybe we can generate insights out of it. Save points, checkpoints. I didn't mention any of this during the presentation, but they could be a little improved. But state processor, I don't know if you heard about that in the previous sessions. This is a wonder. This gives you unlimited access to your state through the checkpoints and the save points that you have. So backfilling, migrations, everything could be so much easier with this. And actually, this will possibly allow us to ditch queryable state and just use state processor to open up the state to the outside world. There will be a little bit of delay here, as as it stands with the current implementation, because this is playing with the checkpoints and save points. So let's say your interval is 30 seconds, you will have a 30-second delay at least. Yes. So now we developers are kind of used to what the data flow implies in our development workflows. Now I think it's time to build up some organization and domain implications on top of this kind of paradigm. Yes, that's it. Thank you.
What are the operational impacts of using Flink this way compared to what we normally think of doing with Flink? Anything change?
I cannot express any relationship or any information to my business people when I'm using just data flow primitives. But this way, I can actually show my business people that, hey guys, this is what it looks like. Now we have those concepts that we can very easily think about. You know, I can conceptualize the bit of client proofreaders. What it means to me, I know what it means to be. It's just 2 words, client proofreaders. I know how to use it. So, and now I have an invitation module that I can just replicate in my mind very quickly. I think the implication for the operation, do you mean like deployment kind of operation?
Yeah.
No difference. All of this is, to me, just sugar, just syntactic changes. The execution graph doesn't change at all. And I showed you the watered-down implementation of this abstract business operator, but it also does automated backfilling and some migration, state migrations and stuff on its own. All right. Thank you, everyone, for joining.
Thank you again.
Thank you, David.